Alright guys, welcome back. This is probably the last lesson for the Algebra 1. So we have reached the end of this series. So today what we are going to learn is called irrational numbers.
Irrational numbers
Alright, let's get into it and say what it is, or what's the definition for irrational numbers.
Let's talk a little bit about rational numbers. Rational numbers. And the simple way to think about it is any number that can be represented as the ratio of two integers is a rational number. So, for example, any integer is a rational number. 1 can be represented as 1 over 1, or as -2 over -2, or as 10,000 over 10,000. In all of these cases, these are all different representations of the number 1, ratio of two integers. And I obviously can have an infinite number of representations of 1 in this way, the same number over the same number. The number -7 could be represented as -7 over 1, or 7 over -1, or -14 over +2, and I could go on and on and on and on. So -7 is definitely a rational number. It can be represented as the ratio of two integers. But what about things that are not integers? For example, let us imagine, let's imagine 3.75. How can we represent that as the ratio of two integers? Well, 3.75, you could rewrite that as 375 over 100, which is the same thing as 750 over 200. Or you could say, hey, 3.75 is the same thing as 3 3/4, So let me write here, 3 3/4, which is the same thing as, that's 15 over 4. 4 times 3 is 12, plus 3 is 15. So you could write this. This is the same thing as 15 over 4. Or we could write this as -30 over -8. I just multiplied the numerator and the denominator here by -2. But just to be clear, this is clearly rational. I'm giving you multiple examples of how this can be represented as the ratio of two integers. Now, what about repeating decimals? Well, let's take maybe the most famous of the repeating decimals. Let's say you have 0.333, just keeps going on and on forever, which we can denote by putting that little bar on top of the 3. This is 0.3 repeating. And we've seen, and later we'll show that how you can convert any repeating decimal into a rational as the ratio of two integers. This is clearly 1 over 3, or maybe you've seen things like 0.6 repeating, which is 2 over 3. And there's many other examples of this. And we'll see any repeating decimal, not just one digit repeating, even if it has a million digits repeating, as long as the pattern starts to repeat itself over and over and over again, you can always represent that as the ratio of two integers. So I know what you're probably thinking. Hey, Sal, you've just included a lot. You've included all of the integers. You've included all of non-repeating decimals, or you've included all of finite non-repeating decimals, and you've also included repeating decimals. What is left? Are there any numbers that are not rational? And you're probably guessing that there are. Otherwise, people wouldn't have taken the trouble of trying to label these as rational. And it turns out, as you can imagine, that actually some of the most famous numbers in all of mathematics are not rational. And we call these numbers irrational. Irrational numbers. And I've listed just a few of the most noteworthy examples. Pi, the ratio of the circumference to the diameter of a circle, is an irrational number. It never terminates. It goes on and forever, and it never repeats. E, same thing, never terminates, never repeats. It comes out of continuously compounding interest. It comes out of complex analysis. E shows up all over the place. Square root of 2, irrational number. Phi, the golden ratio, irrational number. So these things that really just pop out of nature, many of these numbers are irrational. Now you might say, okay.
All right. So far as I could say, the irrational numbers is just a number that goes on. It never ends and it never terminates itself. And all those numbers after the little point are really nice. You can see a pattern inside of that series of numbers. But for the rational numbers, you could always represent that integer with a beautiful equation. Let's say like this one. Okay, that's basically different about them. One is indeed have patterns. Another one does not have a pattern. So that's why we call it irrational. Then we come out with a few stuffs. For example, what's the property for two rational numbers when we add them together or product them together? What's the type of the output?
What I want to do in this video is think about whether the product or sums of rational numbers are definitely going to be rational. So let's just first think about the product of rational numbers. So if I have one rational number, and actually instead of writing out the word rational, let me just represent it as the ratio of two integers. So I have one rational number right over there. I can represent it as a over b, and I'm going to multiply it times another rational number, and I can represent that as the ratio of two integers, m and n. And so what is this product going to be? Well, the numerator, I'm going to have am, I'm going to have a times m, and in the denominator, I'm going to have b times n. Well, a is an integer, m is an integer, so you have an integer in the numerator, and b is an integer, and n is an integer, so you have an integer in the denominator. So now the product is the ratio of two integers right over here, so the product is also rational. So this thing is also rational. So if you give me the product of any two rational numbers, you're going to end up with a rational number. Let's see if the same thing is true for the sum of two rational numbers. So let's say my first rational number is a over b, and that my second, or can be represented as a over b, and my second rational number can be represented as m over n. Well, how would I add these two? Well, I can find a common denominator, and the easiest one is b times n. So let me multiply this fraction. Let me multiply this one times n in the numerator and n in the denominator. And let me multiply this one times b in the numerator and b in the denominator. Now we've written them so they have a common denominator of bn. And so this is going to be equal to an plus bm all of that over b times n. So b times n we've just already talked about. This is definitely going to be an integer right over here. And then what do we have up here? Well, we have a times n, which is an integer. B times m is another integer. The sum of two integers is going to be an integer. So you have an integer over an integer. You have the ratio of two integers. So the sum of two rational numbers is going to give you another. So this one right over here was rational, and this one right over here is rational. So you take the product of two rational numbers, you get a rational number. You take the sum of two rational numbers, you get a rational number.
And again, you're going to prove that the product of rational and irrational number is irrational. Yeah, that makes sense because for an irrational number, no matter what you add to it, or no matter what what product you give to it, or no matter what kind of thing you come with it, you will always get the irrational because it has no patterns out there.
What I want to do in this video is do a quick proof that if we take a rational number and we multiply it times an irrational number, that this is going to give us, that's going to give us an irrational number. an irrational number. And I encourage you to actually pause the video and try to think if you can prove this on your own. I'll give you a hint. You can prove it by a proof through contradiction. Assume that a rational times an irrational gets you a rational number, and then see by manipulating it whether you can establish that all of a sudden this irrational number must somehow be rational. So I'm assuming you've given a go at it, so let's think about it a little bit. I said we will do it through a proof by contradiction. So let's just assume that a rational times an irrational gives us a rational number. So let's say that this, to represent this rational right over here, let's represent it as the ratio of two integers a over b. And then this irrational number, I'll just call that x. So we're saying a over b times x can get us some rational number. So let's call that m over n. Let's call this equaling m over n. So I'm assuming that a rational number, which can be expressed as the ratio of two integers, times an irrational number, can get me another rational number. So let's see if we can set up some form of contradiction here. Well, let's solve for the irrational number. The best way to solve is to multiply both sides times the reciprocal of this number right over here. So this was multiplied times b over a, times b over a, times b over a. And what are we left with? We get our irrational number x. Being equal to m times b, or we could just write that as mb over na. So why is this interesting? Well, m is an integer, b is an integer, so this whole numerator is an integer. And then this whole denominator is some integer. So I've just, right over here, I have a ratio of two integers. So I've just expressed what we assumed to be an irrational number. I've just expressed it as the ratio of two integers. So now we have x must be rational. And that is our contradiction because we assumed that x is irrational. And so, therefore, since this assumption leads to this contradiction right over here, we cannot, this assumption must be false. It must be that a rational times an irrational is irrational. A rational times an irrational is irrational.
All right, problem solved. So all we have to do is to conclude
this assumption.
Let's say how they call it. All we have to do is to conclude a contradiction. Then if that contradiction happen, then we say the old assumption is wrong. Okay, let me just watch this video.
In a previous video, we used a proof by contradiction to show that the square root of 2 is irrational. What I want to do in this video is essentially use the same argument, but do it in a more general way to show that the square root of any prime number is irrational. So let's assume that p is prime. And we're going to set this up to be a proof by contradiction. So we're going to assume that the square root of p is rational, and see if this leads us to any contradiction. So if something is rational, that means that we can represent it as the ratio of two integers. And if we can represent something as the ratio of two integers, that means that we can also represent it as the ratio of two co-prime integers, or two integers that have no factors in common, or that we can represent it as a fraction that is irreducible. So I'm assuming that this fraction that I'm writing right over here, a over b, that this right over here is an irreducible fraction. You say, well, how can I do that? Well, this being rational says I can represent square root of p as some fraction, as some ratio of two integers. And if I can represent anything as a ratio of two integers, I can keep dividing both the numerator and the denominator by the common factors until I eventually get to an irreducible fraction. So I'm assuming that's where we are right here. So this cannot be reduced. And this is important for our proof. cannot be reduced, which is another way of saying that A and B are co-prime, which is another way of saying that A and B share no common factors other than 1. So let's see if we can manipulate this a little bit. Let's take the square of both sides. We get P is equal to, well, A over B, the whole thing squared, that's the same thing as A squared over B squared. A squared over B squared. We can multiply both sides by B squared, and we get B squared times P is equal to A squared. Is equal to A squared. Well, what does this tell us about A squared? Well, B is an integer, so B squared must be an integer. So an integer times P is equal to A squared. Well, that means that P must be a factor of A squared. So let me write this down. So A squared is a multiple of A squared is a multiple of P. Now, what does that tell us about A? Does that tell us that A must also be a multiple of P? Well, to think about that, let's think about the prime factorization of A. Let's say that A can be and any number can be rewritten as a product of primes.
Oh my God, sorry here, guys. I just lost my mind a moment ago, so I just go back to say if I can follow it or not.
So if something is rational, that means that we can represent it as the ratio of two integers. And if we can represent something as the ratio of two integers, that means that we can also represent it as the ratio of two co-prime integers, or two integers that have no factors in common, or that we can represent it as a fraction that is irreducible. So I'm assuming that A, this fraction that I'm writing right over here, A over B, that this right over here is an irreducible fraction. You say, well, how can I do that? Well, this being rational says I can represent square root of P as some fraction, as some ratio of two integers. And if I can represent anything as a ratio of two integers, I can keep dividing both the numerator and the denominator by the common factors until I eventually get to an irreducible fraction. So I'm assuming that's where we are right here. So this cannot be reduced. And this is important for our proof. Cannot be reduced, which is another way of saying that A and B are co-prime, which is another way of saying that A and B share no common factors other than 1. So let's see if we can manipulate this a little bit. Let's take the square of both sides. We get P is equal to, well, A over B, the whole thing squared, that's the same thing as A squared over B squared. A squared over B squared. We can multiply both sides by B squared, and we get B squared times P is equal to A squared. Well, what does this tell us about A squared? Well, B is an integer, so B squared must be an integer. So an integer times P is equal to A squared. Well, that means that P must be a factor of A squared. So let me write this down. So A squared is a multiple of A squared is a multiple of P. Now, what does that tell us about A? Does that tell us that A must also be a multiple of P? Well, to think about that, let's think about the prime factorization of A. Let's say that A can be and any number can be rewritten as a product of primes, or any integer, I should say. So let's write this out as a product of primes right over here. So let's say that I have my first prime factor times my second prime factor all the way to my nth prime factor. And I don't know how many prime factors A actually has. I'm just saying that A is some integer right over here. So if that's the prime factorization of A, what is the prime factorization of A squared going to be? Well, A squared is just A times A. Its prime factorization is going to be F1 times F2 all the way to Fn, and then that times F1 times F2 times all the way to Fn, or I could rearrange them if I want. F1 times F1 times F2 times F2 all the way to Fn times Fn. Now we know that A squared is a multiple of P. P is a prime number. So P must be one of these numbers in the prime factorization. P could be F2 or P could be F1, but P needs to be one of these numbers in the prime factorization. So P P needs to be one of these factors. Well, if it's, let's say, and I'll just pick one of these arbitrarily, let's say that P is F2. If P is F2, then that means that P is also a factor of A. So this allows us to deduce that A is a multiple. A is a multiple of P, or another way of saying that is that we can represent A as being some integer times P. Some integer times P. Now, why is that interesting? And actually, let me box this off because we're going to reuse this part later. But how can we use this? Well, just like we did in the proof of the square root of 2 being irrational, let's now substitute this back into this equation right over here. So we get b squared times p. We have b squared times p is equal to a squared. Well, a, we're now saying we can represent that as some integer k times p. So we can rewrite that as, some integer, write it with this, some integer k times p. And so let's see, if we were to multiply this out, so we get b squared times p, and you probably see where this is going, is equal to k squared times p squared. We could divide both sides by p, and we get b squared is equal to p times k squared, or k squared times p. K squared times p. Well, the same argument that we used, if b squared times p is, if a squared is equal to b squared times p, that let us know that a squared is a multiple of p. So now we have it the other way around. B squared is equal to some integer squared, which is still going to be an integer, times p. So b squared must be a multiple of p. So this lets us know that b squared is a multiple of p. And by the logic that we applied right over here, that lets us know that b is a multiple of p. B is multiple of p. And that's our contradiction, or this establishes our contradiction, that we assumed at the beginning, that a and b are co-prime, that they share no factors in common other than 1. We assumed that this cannot be reduced. But we've just established, just from this, we have deduced that a is a multiple of p and b is a multiple of p, which means that this fraction can be reduced. We can divide the numerator and the denominator by p. So that is our contradiction. We started assuming it cannot be reduced, but then we showed that no, it must be able to be reduced. The numerator and the denominator have a common factor of p.
Okay, so first of all, I have to say that this proof is kind of difficult or kind of complex. Another thing that we could know from this video is a word called, another word called reduced. So this is just another word for simplification, I guess. So if I say this expression can be reduced, in other words, what I have seen is that this expression can be simplified. Alright, so I guess that's today's tutorial. And inside of this tutorial, we have learned about the concept of irrational numbers. And I guess after this video, we could be able to get into a high level of mathematics, no longer staying at the Algebra 1 anymore. So I hope to see you guys in the next one. Bye.